Welcome to SUSECon Digital 22 and session BOV 1280, the convergence of AI and HPC. In this session, we aim to offer a broad overview of the evolution of AI and HPC and look at the technical and business factors driving this convergence. Hi, I'm Terry Smith, Director of Global Partner Solutions here at SUSE.
And I'm Victor Gregorio, Senior Manager of Solution Architects here at SUSE. So we're going to first define what HPC really means in 2022, as it's no longer really confined to supercomputers running simulation codes. In order to define HPC, we should start with the definition of traditional HPC, which is generally supercomputers executing parallel codes for the purposes of simulation and statistical analysis. This is a technology which enables scientists and engineers to run simulations and math models such as computational fluid dynamics, which is very popular in the automotive and aerospace arena. You have things like reverse time migration, which is used for seismic and energy discovery, finite element analysis, which is used by civil engineers, Monte Carlo simulation by the financial sector, and of course, a bevy of simulations that are used by weather and climate analysis and bioinformatics for things like drug discovery and health technologies.
So what do we mean by artificial intelligence, or AI, anyway? In academia, we tend to prefer precise definitions to help eliminate confusion and reduce miscommunication. But AI is a young field, and we are still learning a lot. Even our academic definitions can and do change over time. Today, AI officially refers to any system that perceives its environment and acts upon that environment in a way to maximize the likelihood of achieving an outcome based on past experience or knowledge. By this definition, a self-driving vehicle is AI, actually an integration of AI systems. For example, the car could leverage cameras or LiDAR to scan its environment, recognize a stop sign through past training, and maximize avoidance of receiving a ticket by timely application of its brakes. An expert system, on the other hand, no matter how good it is at helping your automobile mechanic diagnose a bad fuel injector, is not AI by this definition. The industry, or common usage of the term AI, is a bit looser, more focused on function. Here, we define AI as the system that seems to mimic cognitive functions typically associated with a human, or more broadly, a living mind, such as reasoning, pattern recognition, problem solving. Function areas include, but are not limited to, data analytics, natural language processing and speech, vision, diagnostics, optimization, and of course, robotics. These functions have wide-ranging applications that influence our lives every day, from voice-activated navigation systems to movie recommenders to credit card fraud detectors. AI is also helping us solve seemingly intractable problems and speeding us to faster answers. It should be noted that AI can, and often does, require significant computational resources to accomplish these feats. And this is part of the connection with HPC.
That's right. Those functional AI models that Terry's mentioning have made their way into modern high-performance computing, or HPC, in various sectors. You can see it being used in image analysis, which is popular in the retail space or the security realm for physical security, such as airports. You see image analysis being used in HPC with AI in the medical field. Of course, network security is starting to leverage artificial intelligence for automated intrusion detection and monitoring. And of course, the national labs are leveraging AI and HPC for clean energy discovery as well as nuclear safety.
Now let's explore how IT leaders can and are merging HPC and AI. Hybrid HPC AI is real, and it is happening already. For example, AI can be used to refine results of multiple HPC cycles to create ensemble models for complex systems and help us make better predictions, such as the likely path of a hurricane. AI can also improve the speed and accuracy of HPC simulations by learning how to pre-process data for faster or more accurate results.
One of the most popular unified models with HPC and AI is what's called surrogate modeling. And the way this works is that traditional HPC computing might entail for an entire project many iterations of compute runs with sweeps over different input data sets to finally arrive at some result for the entire project. So an AI surrogate model runs an approximation alongside the traditional compute model and runs significantly faster. And through these approximations can narrow the number of traditional HPC runs that are needed for the entire project. The result is that the pairing significantly brings faster time to results for the entire computational project. And as researchers get used to running AI and HPC together, it's important to understand how these environments are similar and how they're different inside of a data center. On the left, we'll look at software and tooling similarities between HPC and AI. They both leverage optimized math libraries, many of which have been developed over decades in support of HPC. In both modalities, production applications tend to be executed by highly technical users. These technical users leverage batch job submission into clustered systems, and they are using Linux containers to facilitate cloud adoption of their compute runs. Finally, in both HPC and AI, users contribute to and enjoy the benefits of open source innovation. In contrast, on the top right, HPC developers often leverage lower level programming languages that excel in floating point computation like Fortran and C. And HPC applications make heavy use of message passing interface implementations to enable tightly coupled clustered computation. Finally, a differentiator in HPC is that the results need to be visualized locally by a scientist or engineer in order to be useful. This can be seen such as a grid of a turbine engine or a wing foil, looking at heat spots or wind marks as a result of an HPC run.
In AI, programmers often leverage higher level languages and even scripting languages like Python, JavaScript, Lua, and others to build complex AI systems from optimized building blocks collected into frameworks and libraries. Some AI, what we call deep learning, is tightly coupled with specialized parallel processors like GPUs. And AI often leaves the typical compute environment, such as interactive websites, home assistants, blockbuster films, and robotic pets. Storage is another area where AI and HPC share many similarities in technology, architecture, and use. Both leverage high-speed data access, often to very large data sets. There is a need to share data across multiple compute resources, and having strict data governance is essential.
As we move up the stack from storage, we'll see that both AI and HPC need high-speed, low-latency specialized networks. These are high-bandwidth networking environments specifically to access data at rapid speeds, low-latency networks required for internode and storage communication. And in both cases, a minor network jitter can crash applications. The complexity of these environments require complex network security configurations and expert staff to configure, monitor, and deploy the environments. As we move even further up the stack, we'll see that there's similarities in the computing power needed by both HPC and AI applications. They both require specialty compute resources such as specialized processors with high core counts or high clock speeds, dense GPUs to facilitate parallel computation, and in many cases, large memory requirements to support faster in-memory computation. All this specialized computing often results in higher power requirements, requiring appropriate cooling and other resources to keep the data center safe.
And let's not forget the business and user benefits of converging AI and HPC. Having separate AI and HPC environments introduces unnecessary costs, duplicating technical and staffing resources. But merging AI and HPC enables businesses to improve CapEx with improved hardware utilization, unified data center resources, optimized spending through better vendor discounts. And in the OpEx side, IT gets unified tooling, integrated access controls and governance, and improved staff utilization.
Unifying HPC and AI environments also unifies governance and security across the entire environment. This enables efficiencies such as a combined system security documentation. It will generally shorten compliance audits. It definitely simplifies disaster recovery planning and generally unifies response policy and incident tracking across the two modalities. Finally, all these efficiencies will optimize security operations tooling and staffing.
Even from the user's point of view, merged AI and HPC enables unified access to compute resources, simplified data management, and new ways to tackle difficult problems. Some basic examples include access to modern AI tooling, such as better container management for HPC users, and very efficient HPC batch processing for AI users. We have discussed some of the drivers of the convergence of AI and HPC, including access to new modes of discovery, potential for CapEx and OpEx savings, and improved user experience. With the cross-pollination of AI and HPC, we can expect to see improved container capabilities to support hybrid workloads, better integration of HPC and AI workloads in agile, enterprise Kubernetes landscapes, and modernization of IT and developer tooling. Links to a few examples of converged HPC and AI can be found in the slide deck. We hope this talk has inspired you to explore this topic further. Thank you for joining us at SUSE Con Digital 22.
Thank you all.